Hi there, my name is Frankie de Brenner. Welcome on this channel on signals, systems and control. Today we will talk about the sampling theorem and the associated undesired effect of frequency folding, also known as the aliasing effect. Well, let us have a look at a first Python animation in which a sinusoidal signal at a frequency f0, it can either be a cosine or a sine, is sampled at a sampling frequency f of s. As you can see, the original sinusoidal signal is shown in blue, whereas the samples at kts, where ts is the sampling period, are shown in orange. Well, as you can see, you can change the sampling frequency and you can also change the frequency of the sinusoidal signal. In first instance, we'll leave f of s, the sampling frequency, constant, and we'll modify f0, the frequency of the underlying sinusoidal input. As you can see, the signal frequency f0 is represented on the x-axis of the second plot, and the perceived frequency is represented on the y-axis. As you can see in the present configuration, so f0 is equal to 30, you can see that, well, the perceived frequency is also 30 Hz. So f0 is equal to its perceived frequency. Well, this is why we're in this green region. This green region is the region where the perceived frequency is equal to the original frequency f0. But what do we mean with perceived frequency? Well, the perceived frequency is the frequency of the sinusoidal signal with smallest frequency that goes through the samples that you can see over here. So there is no sinusoidal signal with frequency smaller than 30 Hz and the frequency of the original signal that goes through the samples. Notice that for a fixed perceived frequency, let us take the value of 30, there are other sinusoidal signals of higher frequency than f0 that go through the same samples. You can see it clearly that a signal with frequency 70 Hz will also go through the same samples. Let us have a look. If we type 70 over here, we see that the samples haven't changed. Okay, in blue you see now the sinusoidal signal at a frequency of 70 Hz, but this signal is now perceived at a frequency of 30 Hz, right? You can go even further. If you continue, you meet here the frequency 130 Hz, and you can see indeed that, well, this high frequency sinusoid goes through the same samples and is again perceived at 30 Hz. You can continue with frequencies at 170 Hz, 230 Hz and 270 Hz, or even further if you wish to continue. We can see that there is a limit here beyond which the frequency f0 is no longer perceived at f0. So let us try with 40 Hz. As you can see, well, it's still perceived at 40 Hz. 50 Hz is still okay. There is no sinusoidal signal of frequency lower than 50 Hz that will go through the samples. But as soon as you pass here this limit frequency of 50 Hz, well, let us try 60 for instance. Well, the signal is now perceived at a lower frequency. Notice that this limit frequency, 50 Hz, corresponds to the sampling frequency divided by 2. And this limit frequency, we'll call it the Nyquist frequency. So if f0 is smaller or equal to the Nyquist frequency, then everything seems to be okay, in the sense that the frequency f0 will be perceived as such. This green zone here, where f0 is equal to the perceived frequency, is called the first Nyquist zone, right? and these are the second, third, fourth, and so on Nyquist zone. Notice that in the odd Nyquist zones, this one, and this one, the perceived frequency is increasing with increasing frequency, while in the even Nyquist zones, this one, and this one, the perceived frequency is decreasing with increasing f0. Notice also that the perceived frequency is always smaller than, well, in this case 50 Hertz, which corresponds to the sampling frequency divided by 2. So the perceived frequency is always smaller than the Nyquist frequency. Later on in the video, we'll see how this second plot is obtained using an interpretation in the frequency domain. So previously what we have done is kept the sampling frequency fs constant and changed f0. What we'll do right now is do the inverse, right? We'll keep f0 constant and we'll modify f of s, and then we'll have a relation between the perceived frequency and the sampling frequency. Well, in this interpretation there is no change, of course, in the first plot, and in the second plot what you can see here is the sampling frequency that has been selected over here. The green line corresponds to the so-called Nyquist frequency, so that's half of the sampling frequency, right? And here you have two lines, a blue one which is the frequency of the original sinusoidal signal, and a purple one which corresponds to the perceived frequency. And in this case, with the sampling frequency of 100 Hertz, well, the perceived frequency is equal to the frequency f0 of 30 Hertz. So again, we have a frequency region that is indicated here in green, where the sampling frequency is such that the perceived frequency is equal to the original frequency f0. Again, we see that there is a limiting frequency for f of s, and below this frequency, the perceived frequency will no longer be equal to the original frequency f0. We'll start by decreasing the sampling frequency to 80 Hertz. You can see that this is still okay. The perceived frequency is equal to 30 Hertz, which is f0. Let's take 60 Hertz, and as you can see, this is the limiting situation over here, but still the perceived frequency is still 30 Hertz. There is no sinusoid of frequency smaller than 30 Hertz that will go through the samples. But now if we still decrease, for instance, to 50, we see that the perceived frequency is now at 20 Hertz. There is a sinusoidal signal with frequency 20 Hertz that goes through the samples, so the perceived frequency is lower than the actual frequency of 30 Hertz. By the way, in blue you can see f0, in magenta the perceived frequency, and in green here the Nyquist frequency, which is half the sampling frequency, and this corresponds to 25 Hertz. And as you will see, the perceived frequency is always smaller or equal to the Nyquist frequency. So let us have a look at what happens when the sampling frequency decreases. Now the signal is perceived at 10 Hertz. Let us, for instance, go to 30 Hertz. Now the signal is perceived at a constant signal, a signal at 0 Hertz. And let us take another one, for instance 20 Hertz here, and here the signal is perceived at 10 Hertz. In this case, the perceived frequency is equal to the Nyquist frequency. So we see that everything is okay. That is, that the perceived frequency is equal to f0, in this case 30 Hertz, when the sampling frequency is larger or equal to 60 Hertz, and 60 Hertz is 2 times f0. Okay, so fs, sampling frequency larger than 2 times f0, is the same as the Nyquist frequency larger or equal than f0, and this is precisely what we had found previously. Let us summarize these results that we have just obtained, and these results are known under the name Nyquist sampling theorem. Here we work with a sinusoidal signal of frequency f0. Well, this Nyquist sampling condition says that the sampling frequency fs must be at least twice the frequency f0 of the sinusoidal signal. Okay, and this is how you write it mathematically. You obtain an equivalent condition if you divide this equation by 2, and then you have the Nyquist frequency appearing on one side and, well, the original frequency f0 on the other side. So equivalently, you can say that, well, the Nyquist frequency fn must be at least the frequency f0 of the signal. In the time domain, we can say that you should have more than 2 samples per period t0, and of course t0 is related to f0 by the relation 1 over f0. If this Nyquist sampling condition is not satisfied, the perceived frequency will not be f0. Okay, it will be lower than f0, and it will be at most the Nyquist frequency, and we speak of aliasing that is occurring. Well, let us go over the sampling issues again. Here we have a signal of frequency f0 sampled at a sampling frequency fs. You can clearly see that the Nyquist condition is satisfied because you have more than 2 samples per period. But an infinity of distinct sinusoidal signals can coincide on the same discrete samples. And, well, these signals, you can actually construct them. Here n is an integer. Well, all those signals over here, and as I said, well, it's an infinite amount of signals. Well, they are identical at the discrete samples kts. Here k again is an integer. How can you see this? Well, if you write this signal at kts, you plug in kts over here, and then you expand what is in the sign, you will see that fs and ts will cancel out, okay, because ts, for instance, is 1 over fs. So ts and fs cancel out, and inside this sign, well, the second term is a multiple of 2 pi. Okay, so this sign is equal to this sign over here, and this is really the original signal at the discrete samples kts. So we have just shown that there are an infinite amount of distinct sinusoidal signals that coincide on this same discrete samples. Well, let us have a look at a few of those signals. Here is the one that corresponds to n is equal to -2. Here in green, n is equal to -1. In red, n is equal to 1, and in cyan, n is equal to 2. Notice that all those 5 signals are going through the same discrete samples, but the frequency that is perceived here is f0. Okay, so the perceived frequency is f0, and this is precisely because the Nyquist condition is satisfied. So the frequency of the sinusoidal signal with smallest frequency that goes through the samples is f0 in this case. Well, let us have a look at another sinusoidal signal of frequency f0 sampled at fs. Here you can see that the Nyquist condition is not satisfied, because remember that in a period you need more than 2 samples per period, and this is clearly not satisfied over here. So what you can do is have a look at this infinity of distinct sinusoidal signals that coincide on the same discrete samples, and their expression is given over here. So this is the signal that corresponds to n is equal to -2. Here's the one that corresponds to n is equal to -1, n is equal to 1, and n is equal to 2. And here you can see that the perceived frequency is lower than f0? Well, it's the frequency that comes from this sinusoidal signal with n is equal to -1. And this is precisely because the Nyquist condition is not satisfied. So the frequency of the perceived signal, that is the frequency of the sinusoidal signal with frequency that is the smallest and that goes through the same discrete samples as the original signal, has a frequency that is lower than f0, and here we have aliasing. So is it possible to compute the perceived frequency? Remember that all those sinusoidal signals go through the discrete samples, right? And they have a frequency f0 plus n times the sampling frequency. We need to look for the frequency that is such that, well, this quantity in absolute value is the smallest, right? And we know from what we have seen before that the perceived frequency is smaller or equal to the Nyquist frequency. So this is the condition that we have in order to find the perceived frequency, and this will produce us an n. Notice that if the Nyquist condition is satisfied, well, you'll have n is equal to 0 over here. Remember that the n that we're looking for is an integer. So the first thing that we're going to do is to divide by f of s, and this gives us a condition that is equivalent, right? And since we're working with n that are integers, we're going to replace this quantity here by this quantity over here, where n int is the integer closest to x, right? And we're using a rounding half up rule for half integers. So n int of 0.5 is 1. And now, since we're working with integers, and that, well, this quantity is smaller than a half, well, this quantity here, since we're working with integers, must be 0. So we have found that n is, well, minus the nearest integer to f0 over fs. And since we have n now, we can plug it in over here, and the perceived frequency is given by this expression. Notice that the formula of the perceived frequency that we see over here has been used to obtain the second plot in this animation. As you can see here, we obtain the perceived frequency as a function of the sampling frequency, and previously we had, well, the perceived frequency as a function of the sinusoidal signal frequency f0. So far we have looked at interpretations in the time domain, but you can also see things in the frequency domain. Assume that you have a signal y of t and that this signal has a Fourier transform y of f. So this is really a decomposition of the signal in terms of its frequency content. So you'll have on the x-axis the frequencies and on the y-axis the energy or the amplitude, right? Then we can have a look at the Fourier transform of this signal y of t that is sampled at a frequency f of s. And this will produce, after sampling, a signal y of s, the sampled signal. And then you can compute its Fourier transform. And what you can see is that you obtain this result over here. So the Fourier transform of the sampled signal is a superposition of shifted analog spectra. Indeed, what you can see here is that this Fourier transform is actually this one shifted, okay, because you see here plus nfs, and all these, well, Fourier transform are then summed up and multiplied by 1 over ts. So what we'll do right now is look at a frequency domain interpretation using this formula over here. If you want to know more on how you can find this Fourier transform of signal that is sampled, you should look at the literature, or you can look at my video lecture on signals and systems. So let us go back to our Python animation. We still have our sinusoidal signal with a frequency of 30 Hz and a sampling frequency of 100 Hz. What we'll do is check the following boxes over here. What you see here as indicated is the two-sided amplitude spectrum of the sampled signal, and this is obtained from the Fourier transform of the sampled signal. So let us write down again the Fourier transform of this sampled signal, and here it is. So you have a factor 1 over Ts and then a sum ranging from minus infinity to infinity of, well, the original Fourier transform that is now translated to frequencies f plus nfs, and then they are added. So what you can see here in this amplitude spectrum is that the central motive is shifted to the right once, twice, 3 times, to the left once, 2 times, 3 times, 4 times, and so on, and then everything is added, and this is how you obtain this two-sided amplitude spectrum. So as I said, this is here the central motive that corresponds to n is equal to 0, right? And well, it corresponds to the amplitude spectrum of our original cosine. What I must say also is that in this amplitude spectrum, what I did is not take into account this factor over here. Since we're only talking about aliasing effects, this has no effect at all. So let us have a look at this central motive, which is really the amplitude spectrum of our original cosine. As you know, the cosine at 30 Hz can be written like this, and using Euler's formula it can be written like this: the first term and then a very similar term with a minus sign over here. And the interpretation is that this is a phasor of amplitude 1/2, right, turning counterclockwise at a frequency of 30 Hz. And here you have a phasor of amplitude 1/2 turning clockwise at frequency 30 Hz, right? So this information, you see it over here, amplitude 1/2, frequency 30 Hz. This one, you see it over here, frequency minus 30 Hz and amplitude 1/2. And you can clearly see, as I said, that this central motive is repeated. Well, this amplitude spectrum is a two-sided amplitude spectrum. This is because we look at negative and positive frequencies. Since everything here is, well, even, as you can see, and this is because we work with real valued signals, what we'll do is work with a one-sided amplitude spectrum. And this is easily done by unchecking this thing here. And as you can see, we're now only looking at the positive frequencies. What we have done also in this one-sided amplitude spectrum is multiply, well, the amplitudes by 2, right? Since everything is brought back to the positive frequencies, and in this way we also recover the amplitude of our original cosine. This is really the one-sided amplitude spectrum of the sampled signal, but we did not take into account, as I said before, the factor 1 over Ts. Well, remember that the perceived frequency will be lower than the Nyquist frequency, so it will be in the green zone. In this case, because the Nyquist condition is satisfied, what we recover is a frequency from the central motive. So the perceived frequency is equal to f0 is equal to 30 Hz. So what we'll do now is gradually increase the frequency f0 and see what happens. As you've seen, well, this peak here has moved to the right, and this one has moved to the left. This is really 100 minus 40, so this is 60. Here 100 plus 40. Here you have 200 minus 40, and here 200 plus 40. But you can still see that the Nyquist condition is satisfied, so f0 is smaller than the Nyquist frequency. So the frequency that is selected comes from the central motive, and there is no aliasing. f0 appears at 40 Hz as it should. Let us increase the frequency even further to 50 Hz. As you've seen, the blue spike has moved to the right and the light blue one has moved to the left, and they lay on top of one another. But as you can see, we have arrived at the limiting situation. f0 is equal to the Nyquist frequency, so we still have that f0 appears as it should be at 50 Hertz in this case. Well, let us increase the frequency even further to 60, and then you can see that, well, the frequency f0 is now larger than the Nyquist frequency, so the Nyquist condition is not satisfied. We have aliasing, as you can see, right? So the blue spike has moved to the right and the light blue one has moved to the left and is now inside this region that is green, where the frequency is selected, right? So this frequency here is 100 minus 60, right? So 40, and this frequency of 60 Hertz sampled at 100 Hertz appears as a frequency of 40 Hertz, as you can see over here and as you can see over here. As you can see, the selected frequency does not come from the central motive, it comes from the motive that was shifted to the right by Fs. Well, let us now change the value of f0 to a value of 160 Hertz, and if we are right, well, the perceived frequency should still be 40 Hertz. So let's have a look. And indeed we see that this is the case. Here we see the frequency 160, that this comes from our central motive. Of course, f0 is much larger than the Nyquist frequency, so the Nyquist condition is not satisfied, and the selected frequency is this one over here in green, and this comes from the second motive, the one that was shifted to the right by 2 times Fs, so 200, and this frequency is really 200 minus 160, so 40 Hertz. So in conclusion, a sinusoidal signal at a frequency of 160 Hertz sampled at 100 Hertz, as you can see over here, will be perceived as a frequency of 40 Hertz, and as you can read also in this plot over here. In the following plot, we have come back to the situation where f0 is 30 Hertz and fs is 100 Hertz. And what we'll do over here is show why we call this aliasing. But another word that you find is, of course, frequency folding. In this spectrum over here, you can see the different, well, Nyquist zones. This is the first Nyquist zone from 0 to Nyquist frequency, then to Nyquist frequency to 2 times Nyquist frequency. It's the second Nyquist zone, third Nyquist zone, fourth, and so on. And what frequency folding means is that everything is folded back to the first Nyquist zone. So how can you see this? We'll have a parameter here that I can increase, and that will show what will happen. Well, this is what happens, and you can clearly see that everything is folding back to the first Nyquist zone. What I can do now is further increase. Well, you can see now that all the Nyquist zones have folded on one another and have folded on the first Nyquist zone. So If I would increase the value of alpha to 90, they would really lie on top of each other. I will keep this value so that you can see what happens when f0 is increasing. So what I will do is maybe turn this so that you can see things a little bit better. So now we can start increasing f0. So here f0 is in the first Nyquist zone, so it appears at 30 Hertz. This will still be the case if I have 40 over here. Indeed, 40 Hertz is still in the first Nyquist zone, so f0 appears at 40 Hertz in this case. Here we'll have the limiting situation. Well, as you can see, the peak is at the edge of the first Nyquist zone and the second Nyquist zone, but when you fold everything back, it still appears at 50 Hertz in this case. So we do not have aliasing yet. So what we'll do now is increase this value to 60. Well, we have now a frequency of 60. So this frequency is in the second Nyquist zone, but if you fold it back to the first Nyquist zone, it looks as if the frequency is 40 Hertz. So the perceived frequency is 40 Hertz, and this is also what you can see over here. And of course you can continue like that with this idea of frequency folding. Let us take as a last one at 160 Hertz. Well, in this case, the perceived frequency is still 40 Hertz, but this peak at 160 Hertz is in the fourth Nyquist zone, and when you fold it back, it is again folded back to the first Nyquist zone. It is still perceived as a frequency of 40 Hertz. Let's maybe come back to values 45 and minus 45 so that you can indeed see that this frequency here is in the fourth Nyquist zone. As you can see, this frequency f0 at 160 Hertz lies in the first, second, third and fourth Nyquist zone, and when folded back to the first zone, it appears at 40 Hertz. This frequency folding technique to compute the perceived frequency is sometimes used because it is easy to obtain the perceived frequency, and it's also very visual. So far we have only worked with a sinusoidal signal with a frequency f0, but in general a typical signal can contain many frequencies simply because it is the sum of several frequencies, or that the signal is periodic, and in that case you'll have the fundamental frequency and its harmonics, or that the signal is aperiodic, and in that case you'll find a continuum of frequencies. Remember also that signals can be affected by noise, and noise contains many frequencies. For example, white noise contains all frequencies. This is why we have to generalize the Nyquist sampling theorem to general signals. And in this case, we have to replace f0 by the highest frequency f max present in the signal. And the highest frequency present in the signal is also sometimes called the bandwidth. So the sampling frequency fs must be at least twice the bandwidth of the signal, right? And if we work with the Nyquist frequency, the Nyquist frequency must be at least the bandwidth of the signal. When the Nyquist condition is not respected, and that's because there is a frequency above the Nyquist frequency, then it's impossible to distinguish between a frequency f0 that would be, for instance, above the Nyquist frequency and its lower frequency aliases, right? So for instance, if there is high frequency noise present, frequencies of noise above the Nyquist frequency, this noise content will be aliased back to lower frequencies. So to prevent such effects, and when the sampling frequency fs has been fixed, what you should do is pass the signal through an analog low pass anti-aliasing filter. This filter will remove all frequency components above the Nyquist frequency, and in this way you will ensure that the Nyquist condition is met. Of course, this assumes that you're using a perfect anti-aliasing filter, and we know that perfection does not exist, so we'll see what happens if you're using a filter that has a certain order and that leaves maybe some of the high frequency components. Let us now have a look at the next Python animation. As you can see, the blue signal is the one that is going to be sampled, and it's constructed from a fundamental frequency here at 20 Hertz, and also from the second, third and fourth harmonic, right? You can set the amplitude of each frequency, right? And as you can see, you can also add white noise of mean mu and of variance sigma square. Well, the spectrum of the blue signal is computed using the DFT, so that's the discrete Fourier transform, using the fast Fourier transform, which is an algorithm that allows you to compute the DFT, and both will be discussed in one of the next videos in this channel. Well, as you can see, the one-sided spectrum is shown. As you can see, the spectrum is consistent with what we see over here, right? So we can see here the fundamental with an amplitude of 1, second harmonic with an amplitude of 0.8, third harmonic with an amplitude of 0.6, and fourth harmonic with an amplitude of 0.4. The signal in blue, which mimics a continuous time signal, but in this simulation, of course, it's also a discrete time signal, but sampled with a sampling frequency that is much higher than the one you see over here, so it looks like a continuous time signal. Well, this signal in blue has been sampled at a sampling frequency of 200 Hertz, and we did not use any anti-aliasing filter. This has produced here the discrete time sampled signal that you see in orange. Well, it's now possible to compute the spectrum of this sampled signal using, again, the DFT, right? And this is shown over here, and as you can see, well, on this interval from 0 to the Nyquist frequency, it corresponds with the spectrum of the original signal. And this is not a surprise, because as you can see, the Nyquist condition is satisfied. The Nyquist frequency here, 100 Hertz, is larger than the largest frequency that is contained in the signal, and here it's the fourth harmonic, right? And this fourth harmonic is at 80 Hertz, and this is why we did not need in this case an anti-aliasing filter. Well, let us now change the frequency of our fundamental, right, to 30 Hertz and see what happens, right? So I'll first show the spectrum of the original signal in blue. Of course, now as you can see, well, you see 30 Hertz, 60 Hertz, 90 Hertz, and here 120 Hertz. Well, the Nyquist frequency is now smaller than the largest frequency in the signal. So the Nyquist condition is no longer satisfied. And you can see that everything will be okay for these, well, three frequencies, the fundamental and the two first harmonics, right? Harmonic 2 and harmonic 3, but not for harmonic 4. And this is what you see when you look at the spectrum of the sampled frequency. You can see that this frequency here, because of frequency folding, has been aliased back to a frequency of 80 Hertz. An obvious solution is, of course, to make sure that the Nyquist frequency is satisfied again, and therefore we need a Nyquist frequency that is above 120 Hertz. So for instance, if we take a sampling frequency of 300 Hertz, the Nyquist frequency is now at 150 Hertz, and you can see that, well, the spectrum of the sampled signal now corresponds with the spectrum of the original signal on this first Nyquist zone here shown in green. So here we have returned to the situation where we have 200 Hertz sampling frequency and that we have our peak here that is aliased back to 80 Hertz. A second solution would be to use an anti-aliasing filter, and in first instance we'll use an ideal anti-aliasing filter, even if in practice it cannot be implemented, because you need to implement a filter that you can use recursively on the data in real time. But to show things in theory, well, we're going to use this ideal anti-aliasing first. Well, here you see an additional signal appearing, and this is the signal after anti-aliasing filter, right? And once you have filtered the signal, you can then sample it to obtain the signal in orange. So as I said, I'm using here an ideal anti-aliasing filter that you cannot use in practice. So how is it obtained in our case here? Well, for that I'm going to remove the spectrum of the sampled signal. Well, the signal here in magenta is obtained as follows. I take the spectrum of the original signal in blue, remove everything that is above the Nyquist frequency, right? And then you obtain the spectrum here in magenta, and then take the inverse FFT, and this yields the signal in magenta. Of course, when you work in real time, you cannot do this, but at least this illustrates the theory, right? And as you can see now, well, the spectrum of the sampled signal is shown here in orange, and you can see here, of course, that you do not have this frequency that is aliased back. So in this interval from 0 to Nyquist frequency, we see the frequency correctly. Of course, and this is because we have chosen to work with the sampling frequency of 200 Hertz, we cannot see this peak over here, because you can see frequencies only up to the Nyquist frequency, in this case 100 Hertz. So let us see what happens if we do not use this ideal anti-aliasing filter, but one that could be used in practice. In this case, it's a Butterworth filter, but I could have chosen another type of filter. As you can see, the degree of the Butterworth filter is 5 over here. So let us see what happens. Well, let us have a look at the time domain signals. As before, the signal in magenta is the signal after the anti-aliasing filter, and the signal in orange is the sampled signal. So it's the magenta signal that is being sampled at the sampling frequency of 200 Hertz. What is obvious is that, well, the signal in magenta, and of course also the one in orange, is phase shifted. This phase shift will increase with the degree of the filter. In some applications, such as control, this phase shift could of course be really problematic. Well, let us now have a look at the frequency domain, and as you can see over here, well, maybe I should hide the spectrum of the sampled signal. Our anti-aliasing filter has attenuated, okay, everything that is above the Nyquist frequency, but this peak over here is still present, and this is why you can see it in the spectrum of the sample signal. It is being aliased back to a component at 80 Hertz, right? So if we look at things, this is because where our filter here, our Butterworth filter, has an attenuation of -3 dB at the Nyquist frequency, and well, the attenuation here at 120 Hertz is only, well, roughly -10 dB, right? This is why this component is left and aliased back. So what we could do is maybe increase the degree of the filter. As anticipated, we have seen that there is now a larger phase shift in the time domain, okay, and you can see here that the slope is higher, so we have an attenuation that is now, well, roughly -15 dB at 120 Hertz. Okay, and this is why you see here that this component that is aliased back has become smaller. Okay, we can go the other way around and maybe take a degree that is only 1, right? So this is a first order Butterworth filter. The phase shift in the time domain is smaller. Okay, here we have minus 3 dB. We have less attenuation at 120 Hertz. So we see what happens over here. This is this frequency that is aliased back. But we see another effect now. We see also that there is, well, attenuation below the Nyquist frequency, and this is why we see some attenuations here at, well, the frequencies at 30, 60 and 90 Hertz. So you can see that not only the sampling frequency is of importance, but also the type of anti-aliasing filter and its order. So we have come back to our original situation with our fundamental and harmonic 2, 3 and 4 amplitudes are given over here, right? And we are sampling the signal with a sampling frequency of 200 Hertz, resulting in, well, the sampled signal shown in orange. Of course, since the Nyquist condition is satisfied, the spectrum of the sampled signal coincides with the spectrum of the original signal on the first Nyquist zone. This is also the reason why we do not use any anti-aliasing filter. Let us now have a look at the influence of noise. So what I'll do is increase sigma here from 0 to 0.5. And as you can see, well, we have added noise on the original signal before sampling it, right? And what you see here in blue is the spectrum of the original signal. We still see the fundamental and harmonic 2, 3 and 4, but we see here that there is white noise present in the signal. Notice that it's called white because it's present at any frequency. Well, the higher sigma, the higher the noise level in the spectrum, of course. So I'll come back to this value over here, and what we can do now is look at the spectrum of the sampled signal. Okay, so here it is. You can still see the 4 original frequencies, but what you can see here is, well, this high components for the noise in this frequency range from 0 to Nyquist frequency, and this is simply because the noise that is above the Nyquist frequency has been aliased back to the first Nyquist region here shown in green. Of course, what we should do, and I'll first remove here the spectrum of the sample signal, is use an anti-aliasing filter. Again, here I'll use the ideal anti-aliasing filter, and when the signal, the noisy signal in blue, has gone through the anti-aliasing filter here, what you recover is the signal here in magenta, and this one is then used to sample the signal. If you look at the spectrum of the signal in magenta, you can see that it is 0, right, at frequencies above the Nyquist frequency, and it is equal to, well, the original spectrum at frequencies in the first Nyquist frequency zone, so from 0 to Nyquist frequency. And of course, now if I use this anti-aliasing filter before sampling, well, what I'll recover here is really the spectrum of the original signal, right, in the first Nyquist zone, right? And this is really what we want to obtain. What we can do to see things better is zoom in the spectra that we see over here. Here you see the spectrum of the sampled signal. Since the signal has been sampled at a sampling frequency of 200 Hertz, well, you cannot see beyond the Nyquist frequency, which is half the sampling frequency in our case 100 Hertz. In magenta, you see here the spectrum of the signal after anti-aliasing filter. Since we have used an ideal anti-aliasing filter, well, all frequencies above the Nyquist frequency have been removed. And in blue, of course, you see the spectrum of the original signal and the influence of the noise. Well, let us also have a look at this frequency folding analogy and see what happens. First, I'll remove the spectrum of the sampled signal and we'll remove the anti-aliasing filter, and this is what you obtain then. So this is the spectrum of the original signal, and we have sampled with a sampling frequency of 200 Hertz. So you see here the Nyquist zones. So this is Nyquist zone 1 from 0 to 100, from 100 to 200, Nyquist zone 2, etc. And all those, well, Nyquist zones above the first one are going to fold back to the first one, and this is why we're going to see this aliasing effect on the noise. But here we only see really 5 Nyquist zones, but there are many more, right? For instance, I can have a look at 50 of them. So here they are, and what I can do now is fold them back onto the first Nyquist zone. So here they have all folded back, and what I can do is change this parameter here so that we can see things better. What you see here is, of course, the first Nyquist zone with on top of that the 49 other Nyquist zones. My signal in blue that was mimicking the continuous time signal is really a signal sampled at 10 kilohertz. So behind that signal there is a Nyquist frequency of 5 kilohertz. So this is why I've taken really 50 of these Nyquist zones after sampling. But anyway, what will happen now is that this 50 Nyquist zones will add up to produce the spectrum of the sampled signal. So you obtain here the spectrum of the sampled signal that we had obtained before. Of course, if I now use an anti-aliasing filter, well, the 49 Nyquist zones that come after the first one, well, they will not contribute and will left again with what was in the first Nyquist zone, and then we do not have any aliasing of the noise. And this is what you see after some computation time.